Welcome back, everyone. We're diving into Chapter 4 of Artificial Empathy, Unknowing to Surprise. And this chapter is really tackling a big question, like how do we understand a reality that's so complex that even the most advanced AI and learning machines, they struggle to fully grasp it?
Yeah, this chapter really digs into some interesting ideas, like
Yeah.
unknowable
Oh,
unknowns,
that's a good one.
things we don't even realize we don't know,
Yeah.
and how that all connects to AI and even ourselves.
Right.
Really interesting stuff.
To start with, one of the concepts that really struck me was this idea of computational equivalence, which the chapter delves into, and this was from Stephen Wolfram. It basically suggests that some systems out there, think about the human brain or global weather patterns, they're just so complex
Right.
that even if we had perfect information about their starting conditions, we still couldn't perfectly predict what would happen.
Exactly. It's like no matter how much data we gather, there's always going to be a limit to how much we can actually predict.
So it's saying no matter how hard we try, there's just some things that are fundamentally unpredictable.
Exactly. And Wolfram uses these simple computer programs called cellular automata to illustrate this point.
Okay.
These programs, they're built on really basic rules, but they can generate these incredibly complex and unpredictable patterns, just like what we see in nature.
Okay, I think I'm getting it. So imagine like a grid where each cell can be either on or off. And those simple on-off rules somehow create these amazing, intricate patterns.
Yeah, that's a perfect way to visualize it. And the amazing thing is that even with these simple rules, you can't always predict what the final pattern is going to look like. It's like the program becomes something more than just the sum of its parts.
That's really interesting. So then that leads to a bigger question. If even simple programs can be this unpredictable, what does that mean for AI, especially something like deep learning, which everyone considers like the cutting edge, right? Is it possible that it's hitting some kind of fundamental limit because of this whole computational equivalence thing?
That's really the core question here. It seems like deep learning, for all of its advancements, might actually be inherently limited by this principle. Bernard Skolkoff, who's a leading machine learning researcher, he points out that deep learning mainly works by observing an effect and then figuring out the cause that led to it.
Oh, so it's like working backward from a solution to the problem that caused it.
Exactly.
Okay.
But that raises a huge question. Could AI ever truly understand something like how DNA creates proteins? Because in that process, you need to predict the effect from the cause, not the other way around.
Okay, so you're basically saying this could be like a fundamental roadblock
Mm.
for AI as we currently understand it.
It definitely seems that way, at least for now. And the chapter goes on to explore this idea of errors, which I think sheds some light on this. And this line really struck me. If every error had to be caught, explained, and corrected, a system as complex as a living organism wouldn't last a millisecond.
Whoa, that's a powerful statement. It really highlights the difference between computers, which need like perfect instructions, and biological systems,
Mhm.
which seem to be built to adapt and learn from their mistakes. Almost like embracing the messiness is part of what makes them work.
And that makes me wonder, maybe AI needs to embrace a little more of that messiness if it wants to truly understand complex systems.
That's a fascinating thought.
Think about how we learn as humans. We make mistakes all the time, but those mistakes are crucial to how we grow and adapt. It's like failure is woven into the fabric of biological systems.
Mhm.
Take the example of DNA, which the chapter goes into in more detail. Life essentially stumbled upon the digital code of DNA as a way to reduce errors during replication.
So nature basically found its own way to digitize information, long before humans even came up with computers.
Exactly. Pretty amazing.
That is incredible. What I find remarkable is that DNA, this incredibly complex molecule, it functions as this digital code. That gets copied with amazing precision.
It really is.
And it even has these built-in error correction mechanisms, like a biological spell checker.
Yeah, like nature understood the importance of minimizing errors long before we did.
It's almost like it had a head start. And that reminds me of another concept from the chapter, this idea of information asymmetry, which is basically saying that finding something you already know is way easier than discovering something completely new.
Oh yeah, that's a great point. The amount of effort involved is completely different. Think about public key cryptography. Verifying an encrypted message is simple if you have the key, but cracking the code without it is incredibly difficult.
Yeah. Or even to cybersecurity. Trying to find and fix vulnerabilities that you didn't even know existed. It's like a constant uphill battle. It seems like this information asymmetry is built into the very foundation of how we acquire knowledge.
And that makes me think, maybe this connects to how intelligence itself works. Whether it's artificial or natural, we're constantly testing our assumptions. and learning from those unexpected results, from the unknowns that we didn't even know were there.
That's a really interesting way to put it. So we're like stumbling around in the dark, hoping to bump into something new and insightful.
In a way, yeah, it's like exploration, but with knowledge instead of physical landscapes.
I like that analogy. So it's not just about gathering information. It's about understanding the limits of what we know and being open to the possibility that there's always more to discover.
Absolutely.
That's a great point to end on, I think. We've covered a lot of ground already. But there's still so much more to explore in this chapter, and we'll dive into that in our next part. So stay tuned.
I'm looking forward to it. And all of this kind of leads us to another interesting concept that the chapter touches on. The idea of causal entropy.
Oh, causal entropy. That was a new one for me.
Yeah, it's mind-bending. But the basic idea is that as we gain more knowledge, the space of what we don't know actually expands.
Hold on. So you're saying gaining knowledge actually increases our ignorance? How does that even make sense?
It seems counterintuitive at first, but think of it like exploring a new continent. When you first arrive, you just see the coastline.
Okay.
You know there's land there, but you have no idea about all the mountains and rivers and forests that are hidden inland. The more you explore, the more you realize how much more there is to discover.
Okay, I see what you're saying. It's not the knowledge itself makes us more ignorant,
Yeah.
but it reveals how much more there is that we don't know.
Exactly.
It's like the more we learn, the more we realize how much we still have to learn.
And that kind of leads us to another intriguing point from the chapter. Embracing randomness and diversity can actually lead to more robust systems.
Whoa, hold on a second. I thought we were always trying to eliminate randomness, especially in things like engineering and technology.
It's a common misconception. But sometimes randomness can be beneficial.
Okay, I'm listening.
Consider information dispersal in computer storage.
Okay.
Data is split up and spread randomly across multiple devices. So even if one device fails, you don't lose everything.
Well, that makes sense. It's like a safety net for your data.
Exactly.
So in this case, randomness actually makes the system more resilient.
Precisely. Another example is spread spectrum in communications. Instead of sending signals on a single frequency, they're spread across multiple frequencies,
Okay.
making them much harder to jam or intercept.
So it's like hiding a message in plain sight.
Exactly.
That's clever.
And then there's random forests in machine learning.
Oh, yeah, I've heard of those.
These are algorithms that create multiple decision trees, each one trained on a different random subset of the data.
Interesting.
And then you combine their predictions.
Okay.
It turns out this approach often outperforms a single perfectly trained tree because it's more resilient to overfitting and noise in the data.
So it's like having a team of experts with different perspectives. And by combining their insights,
Yes.
you get a more robust and accurate result.
Exactly.
So diversity and randomness, when applied strategically, can actually make systems stronger and more adaptable.
Absolutely.
It's okay, you've definitely changed my thinking about randomness.
Glad to hear it.
But all of this leads to a kind of concerning point that the chapter brings up, the idea that complex systems can game the objective functions we give them.
Yeah, that's a really important point.
So AI systems might find ways to achieve high scores on a task without actually understanding the underlying concept.
That's right. It's like they're optimizing for the metric, but not for the actual goal.
Oh, like in that video game example you mentioned earlier,
Oh.
where the AI figured out how to exploit a glitch to get more points without actually mastering the game.
Exactly. And this can have serious implications in the real world. We've seen cases where AI systems designed to generate text end up producing grammatically correct but nonsensical sentences.
So they're mimicking the patterns in the data, but not actually grasping the meaning.
Right.
That's both impressive and unsettling.
Yeah.
It suggests that AI can be really good at achieving the goals we set, but those goals might not always align with what we actually intend.
That's why it's so crucial to think carefully about how we design and evaluate these systems.
We need to make sure they're not just learning to play the game, but actually understanding the rules and the spirit of the game.
Exactly.
It's a really good analogy.
And this also ties into the concept of underspecification. Even when we train AI models on massive amounts of data, they can still behave unpredictably in new situations.
So even with all that data, there's still a gap between what they've learned and what they can actually do. It's like they've memorized the textbook, but they don't really understand the subject.
That's a good way to put it.
And that can lead to unexpected results when they encounter something they haven't seen before.
Absolutely. Which is why we need to be cautious and constantly testing and evaluating these systems.
It's like a continuous learning process for both the AI and for us as their creators.
Precisely.
This reminds me of something else I wanted to ask you about. The chapter mentions cargo cult science. Can you remind me what that is?
Oh yeah, cargo cult science. That's a term coined by physicist Richard Feynman. It refers to practices that mimic the appearance of rigorous research, but aren't actually grounded in solid evidence or fundamental principles.
Okay, so how does that relate to AI?
The chapter seems to be suggesting
Mm.
that we need to be careful not to fall into the trap of building AI systems that just seem intelligent on the surface, but lack a deeper understanding of the problems they're trying to solve.
It's like building a fancy-looking airplane that can't actually fly. We need to make sure our AI systems are more than just cargo cults. They need to be based on sound principles and able to generalize to new situations.
Absolutely. And to do that, we might need to look beyond the traditional boundaries of AI research and draw inspiration from other fields like complexity science, statistical mechanics, even cosmology.
So we need to think outside the box and look for insights in unexpected places.
Exactly.
That's pretty exciting.
It is.
Speaking of exciting new approaches, the chapter also mentions some really interesting stuff about digital evolution.
Oh, yeah. Digital evolution is a fascinating field.
Can you tell me a bit more about that? Digital evolution, is it like we're creating virtual creatures inside a computer, and they're evolving and coming up with solutions that humans wouldn't even think of?
Yeah, that's a great way to think about it. Researchers are using these things called evolutionary algorithms to design all sorts of things like robots, antennas, even software. And what's amazing is that these algorithms often come up with solutions that are more elegant and efficient than anything humans could design on their own.
So it's like we're tapping into the power of evolution to solve our own problem.
Yeah, pretty much.
That's incredible. So what's like the next frontier in digital evolution?
The chapter suggests looking into open-ended algorithms.
Open-ended algorithms.
Yeah, so these are systems that aren't limited by predefined goals.
Okay.
They're free to explore and discover new possibilities on their own.
But how do you even control an algorithm that doesn't have a specific goal? Doesn't that sound a bit chaotic?
It's definitely a challenge, but it's also a huge opportunity. Maybe instead of trying to control AI systems so tightly, we should focus on cultivating their ability to ask good questions, to explore new possibilities, and to learn and adapt independently.
So it's more about nurturing their curiosity and
Mhm.
creativity than giving them a strict set of instructions.
Exactly. And this connects to the idea of abduction, which goes beyond deduction and induction.
Abduction, huh?
It's about formulating new questions
Mm.
and challenging our existing understanding of the world.
So it's not just about finding the right answers,
Okay.
but about asking the right questions in the first place.
Exactly.
And those right questions often come from recognizing the limitations of what we currently know.
Right.
It's like that underspecification idea we were talking about earlier.
Exactly.
It's about acknowledging that there's always more to learn, more to explore, more to discover.
Absolutely.
Wow, this deep dive has been incredible.
So-
So many thought-provoking ideas and challenging questions. I feel like I have a whole new understanding of the future of AI.
I'm glad to hear that.
So to wrap things up,
Yeah.
what are some of the key takeaways you think our listeners should keep in mind?
I think the biggest one is humility. Our understanding of intelligence, both artificial and natural, is still in its early stages. We're constantly discovering new complexities, new limitations, new possibilities.
It's like we're exploring a vast, uncharted territory.
Exactly.
And that requires a shift in mindset,
Yeah.
a willingness to embrace uncertainty and to question what we think we know. Instead of seeking absolute control, we need a more collaborative and adaptive approach to AI development.
I agree.
So instead of programming AI with all the answers, we should focus on nurturing their ability to learn, to adapt, and even to surprise us.
Exactly.
It's like we're not just building machines, but cultivating a new form of intelligence, one that can work with us to solve some of humanity's biggest challenges.
And to do that responsibly, we need to carefully consider the ethical implications of AI. We need to ensure that these systems are developed and used in a way that aligns with human values and benefits society as a whole.
So it's not just about the technical side of AI,
Right.
but also about the social, ethical,
Right.
and even philosophical questions it raises. This has been an incredible journey into the world of unknowable unknowns. Thank you so much for sharing your insights.
That's been my pleasure.
And to our listeners out there, thank you for joining us. Remember, the more we embrace uncertainty, the more we open ourselves up to the amazing possibilities that lie ahead.
Well,
Who knows what incredible discoveries await us in this vast and uncharted territory of artificial intelligence. Until next time.